Welcome to part 2 of the Unit 2 review. And we had just finished question number 3, the first 3 parts of question number 3 in part 1. This last one wants to discuss the limitations of the range as a measure of dispersion. Since we saw a wide difference between the population range and the population standard deviation. So here, the range only takes into account the smallest and largest values, which is based on its calculation, which does not provide any information Let me just fix that very quickly. Information about the dispersion of the distribution between those values. Right, we saw that the population standard deviation takes the deviations into account when doing its calculation. The range, though, just uses the smallest and largest. Again, the most simplest method of finding a measurement of dispersion. Okay, so moving on. Question number 4. Suppose the customer is purchasing a car. He conducts an experiment in which he puts 10 gallons of gas in the car and drives it until it runs out of gas. He conducts this experiment 15 times in each car and records the number of miles driven, as shown on here on the right. Despite the unfortunate waste of gas in this particular case, we want to describe each data set. That is, determine the shape, center, and spread, rounded to 1 decimal point, as needed. So for this, we are going to do a couple of calculations. We want the mean, median, sample standard deviation, and range. So let us go obtain this data and toss it into StackHunch. So that data is this one. So we are going to go to stat, summary stats, columns. We want the 2 columns. Might as well do them at the same time. We want the mean, sample standard deviation, in this case. We also want the median and the range. And as we could see, we have this information up on here. For car 1, its mean was 249.1 miles per 10 gallons in this case. So miles after that 10 gallons. So 249.1 miles. Standard deviation of 45.1 miles in this case. We then have a median of 251 miles. And we have a range of 149 miles. Then for the car 2, we have a mean of 251.2 miles. We have a standard deviation of 26.9 miles, a median of 246 miles, and a range of 94 miles. So let us put all of that into our document. Okay, so let me just quickly label each one of these. Okay, so for our mean for car 1, we had ourselves a value of 249.1. miles. For the median, that was 251 miles. For the sample standard deviation, that gave us a value of 45.1 miles. And then finally, the range of 149 miles. That's just for car 1. For car 2, we're going to want the mean, median, median, sample standard deviation, and the range for car 2. So from what we saw, we had a mean of 251.2. miles. We had a median of 246 miles. A sample standard deviation of 26.9. And a range of 94 miles. So, based upon all of these, we could see that car 1 has a much wider spread than car 2, right? We could see that the mean for car 1 is less than the median, and the mean for car 2 is greater than the median, right? So based upon these values, we could claim that car 1 is, because car 1's mean is less than the median, so that means this is skewed left. So we would predict. And for car 2, its mean is greater than the median, so we are going to predict that to be skewed right. based upon the point that this mean is greater than our median. And then which car would the customer buy and why? Well, this would be car 2. Because it has a lower
This device isn't set up yet.
sample standard deviation.
On a phone or tablet.
Sample standard deviation. Hence, more predictable gas mileage. More predictable gas mileage in this particular case. So then, moving off to question number 5. We have scores of an IQ test have a bell-shaped distribution with a mean of 100 and a standard deviation of 16. Using the empirical rule, we want to determine the following. What percentage of people has an IQ? What percentage of people have an IQ score between 68 and 132? So what percentage of those people has an IQ score between 68 and 132? Well, we need to see how many times do we add 16 to 100 to get a value of, let's say, 132. Well, solving this algebraic equation, we just get an answer of 2. Right, and the same thing with subtracting. We have to subtract 16 twice to get 68. So based upon the empirical rule, with a k here of 2, we get an answer of 95% of those IQ scores between 68 and 132. For the percentage of people with an IQ score of less than 60 or greater than 132, well, as we saw, we take 100%, subtract our 95%. That means 5% will have an IQ score of less than 68 or greater than 132. And then finally, we want what percent of people has an IQ score of greater than 116. So we need to find how many times do we add 16 to 100 to get a value of 116. Well, k here is 1. Okay, so for this, it might be helpful to kind of draw this out. So a mean of 100 is here. A value of 116 would be here-ish. And we want to know what this percentage here is, the shaded region. Right, based on the empirical rule, we had 68% was within 1 standard deviation. So since this is symmetrical, we could take half of that to get 34%. But since this is symmetrical, we know that this entire part here, all of this, must add to be 50%. So we could take 50%, subtract 34% to get our answer of 16%. Or we could just add up the respective portions from the empirical rule to get the same answer as well. Moving along, we have for question number 6. 1 year, Alex had the lowest ERA earned run average. Mean number of runs yielded per 9 innings pitched of any male pitcher at his school with an ERA of 3.18. Also, Sally had the lowest ERA of any female pitcher at the school with an ERA of 2.63. For the males, the mean ERA was 4.196 and the standard deviation was 0.599. For the females, the mean ERA was 3.924, and the standard deviation was 0.921. Find their respective z-scores. Which player had the better year relative to their peers, Alex or Sally? And as I note, in general, the lower the ERA, the better the pitcher. So for Alex, for his z-score, we take his value, which is 3.18, minus the mean of the males, 4.196, divided by the standard deviation for the males of 0.599. Rounding this to 2 decimal points, this is negative 1.70. And then for Sally, hers would be, her value is 2.63 minus 3.924 divided by 0.921. Rounding that gives us a value of negative 1.40. So based upon this, we could see Alex has the lowest ERA here. Sally's is a bit higher. So because of this, Alex has a better year because his z-score is lower. Let me just fix that W very quickly. Back. So Alex had a better year because his z-score was lower than Sally's. And then finally, I have question number 7 here on the bottom. Explain the meaning of the 10th percentile of the weight of males 36 months of age in a certain city is 13.0 kilograms. This means that 10% of 36-month-old males weigh 13.0 kilograms or less. Of course, that also means that 90% weigh more. Based on the interpretation of the percentile, 10% of the 36-month-old males weigh 13 kilograms or less. So that is it for our second part of this Unit 2 review. And I will see you for the third part in a moment. Thank you.